Today's lesson is about GCF and LCM. GCF, as you see here on the screen, stands for greatest common factor. Let's find the GCF of 12 and 18. As you know, 12 can be written as 1 times 12, 2 times 6, and 3 times 4. Therefore, 1, 2, 3, 4, 6, and 12 are all factors of 12. Likewise, I'm going to find all of the factors of 18. 18 can be written as 1 times 18, 2 times 9, 3 times 6. So therefore 1, 2, 3, 6, 9, and 18 are all factors of 18. Now, let's figure out the common factors. 1 is a common factor. What else? 2 is a common factor because it appears in both sets. 3 also can be found in both of them, and the last common factor would be 6. So therefore, common factors are 1, 2, 3, 6. And which one is the greatest common factor? Obviously, 6 is the greatest common factor. This is why we use this notation of GCF of 12 and 18 is equal to 6. Let's have another example. Let's figure out the GCF of 48 and 72. 48 is equal to 1 times 48, 2 times 24, 3 times 16, 4 times 12, and 6 times 8. This is why 1, 2, 3, 4, 6, 8, 12, 16, 24, and 48 are the factors of 48. So 72 likewise is equal to 1 times 72, 2 times 36, 3 times 24, 4 times 18, 6 times 12, 8 times 9. Yeah, that's all. 1, 2, 3, 4, 6, 8, 9, 12, 18, 24, 36, and 72 are the factors of 72. Now let's mark the common factors. 1, 2, 3, 4, 6, 8, 12, and 24. Yeah, 24 is the largest or greatest common factor. Therefore, I'm going to finish up this example by writing GCF of 48 and 72 equals 24. So there is nothing wrong with this method. However, it's not very efficient. What if I ask you to find the GCF of, for example, 1200 and like 500? It takes forever to write down all the factors and then mark the common factors. This is why we need a better way, smarter way to find GCF of two given numbers that are fairly big, right? This is why we use standard prime factorization. I'm going to find the GCF of 48 and 72 by applying standard prime factorization in the next slide. So 48 is 6 times 8, 2 times 3. Hope you remember that we encircle the prime numbers where we stop breaking down numbers, right? 2 times 4, and finally 4 is 2 times 2. Therefore, 48 can be written as, so how many 2's can be seen here? 4 of them. Therefore, 48 is 2 to the power of 4 times 3. 72, 9 times 8, 3 times 3, 2 times 4, 2 times 2. 72, therefore, can be written as 2 to the power of 3 times 3 to the power of 2. Now, this is how we determine the greatest common factor. First, we cross out numbers that they are not, bases that they are not in common, but we don't have such thing here because we have base of 2 here. We also have it here. We have the base of 3 here. Also here we have 3. Now, I'm going to write here the common bases, which are 2 and 3, and then I choose the lowest exponents. For example, what does that mean? Look, here the exponent of 2 is 4, and here the exponent of 2 is 3. So I'm going to choose the lowest one, which is 3. The exponent of 3 here is 1. When you can't see anything here, it's invisible 1. And the exponent of the 3 here is 2. So which one is the lowest? Obviously 1. Therefore, I'm going to write here 1. Now let's figure out, let's evaluate this. So 2 to the power of 3 is 8, and 3 to the power of 1 is 3. 8 times 3 is 24. See, we got the same answer with a better way by applying standard prime factorization. I'm going to give you another example. Let's find out the GCF of 400 and let's say 360. Quickly, we'll do here the standard prime factorization. So 40 times 10, 5 times 8, 2 times 4, and finally 2 times 2. 2 times 5. Therefore, 400 is equal to 2 to the power of 4. I see 4 2's. Also, I see 2 5's. Okay, now we'll do the same process for 360. 36 times 10, 4, 9, 2, 2, 3, 3, 2, 5. That gives us 1, 2, 3 2's. Also 2 3's and 1 5. I'm going to write it as 5 to the power of 1. Okay, so in this question, 2, look at the base of 2 here. We also have 2 here. So 2 appears in both of them. 5 likewise appears in both of them here. But we don't have base of 3 in the factorization of 400. This is why we cross out the one that is not in common. Now focus on 2 and 5. I'm going to write here 2 times 5. Now you need to compare the exponents between 2 and 3. We choose the lowest one, which is 3. Look at the exponents of 5's and compare them. 5, 2, 5, 1. So 1 obviously is smaller. This is why I'm going to write here 1. So let's evaluate this. 2 to the power of 3 is 8 times 5, which is 40. So this question has been completed, and GCF of 400 and 360 equals 40. So this method, as I mentioned before, is very quick, very accurate, and you do not need to write down all of the factors, which is a very, difficult task if numbers are fairly, large. Okay, so likewise, we can find LCM of two numbers with these methods. First, I'm going to find the LCM of two small numbers, but before that, we need to see what L, C, and M stand for. So L stands for least common multiple. Okay, let's figure out the LCM of 4 and 6. First thing, we'll write down here all the multiples of 4 from least to the greatest. So multiples of 4 means 4 times 1, which is 4, 4 times 2, 8, 4 times 3, 12, 4 times 4, 16, and as you see, they go up by 4. So 20, 24, and etc. I'm going to write here the multiples of 6. So 6 times 1, 6 times 2, 12, 6 times 3, 18, 6 times 4, 24, and so on. So As you see, we have like infinitely many multiples for any number. So unlike the factors that we have like finite number of factors, the number of multiples never stop and it goes forever. This is why we have infinitely many common multiples. For example, common multiples, I'm going to mark them here, 12 and then 24. And think about it, it goes up by 12 by 12. So the common multiples are 12, 24, 36, 48, and it never stops. So which one is the least common multiple? Obviously 12 is the least number among the multiples. This is why the LCM of 4 and 6 is equal to 12. Next example is about the LCM of 12 and 18. So we need to write down all the multiples of 12 and then find a pattern. Quickly you will dislike this because you need to write 12 times 2, 24, and 36, and then 48, and then 5 times 12, 60. And sometimes you need to go up like painfully for like many more to find out the common multiple, and that's not a good idea to apply this method. This is why we have better methods, but let's try this. 18 times 2 is 36, 18 times 3 is 54, and so on. So here 36 is the least common multiple, but the other multiples also go up by 36, but I'm not going to write more of them because it's cumbersome. So LCM of 12 and 18 equals 36. But the question that needs to be answered is that what if the question is about finding the LCM of 1200 and let's say 450. Obviously, that's like not easy to apply this method to find the LCM of those huge numbers. This is why we again will use standard prime factorization to find the LCM of two numbers. Okay, I'm going to find the LCM of 12 and 18 by applying the standard prime factorization. So 12, 2 times 6, 2 times 3. Therefore, 12 is equal to 2 squared times 3. So now 18 is 2 times 9 and 3 times 3. So 2 to the power of 1 actually, like 3 to the power of 1 here, times 3 squared. Now, look at the common bases. 2 and 2 appears in the both factorizations, also 3 and 3 here. So we write them down here. Unlike the GCF, you will choose the maximum exponents. So you compare the exponents of 2 which are 2 and 1, and you choose the largest one, which is 2. Also, between 1 and 2, 2 is bigger. This is why we choose 2 here. Now let's evaluate this one. 2 squared is 4 and 3 squared is 9. So 4 times 9 is 36. This is the exact answer that we got with another method. Let's have another example. I'm going to find out what the LCM of 520 and 420 looks like. So 520 is 52 times 10. 52 is 4 times 13, and 13 is a prime number. So 2 times 2 and 2 times 5. So 520 is 2 cubed times 5 times 13. 420 also can be written as 42 times 10 and 6 times 7. 7 is prime. 2 times 3, 2 times 5. So if we put together 2's, we have 2 2's. We have also 1 3, and also we have 5 and 7. I think the standard prime factorization is completed now. And now this is how we determine the LCM. So 5 and 2 are common bases in both of them. But 3, 7, and 13 are not common bases. So this is how you get the LCM. First, you write those numbers that are not in common. Just copy them down. So 3 times 7 times 13. Now time to deal with those numbers that are in both factorizations, like 2. So you write 2 here, and also you write 5 here. But let's compare the exponents. The exponent of 2 here is 3, and here is 2. Unlike the GCF, you choose the largest exponent. Therefore, we'll choose the exponent of 3 here for 2, and then we'll choose the exponent of 1 for 5, because both 5's in both factorizations have the same exponent, 1. This is GCF. That's a huge number. If you use your calculator, you can find the final answer, which is 3 times 7 times 13 times 2 to the power 3 times 5. So it's going to be 10920. And let's take a look at the last example. You are given the standard prime factorization, and you do not need in this example to break the numbers down. So we are going to find the LCM of 2 to the power of 3 times 5 to the power of 2 times 7 and 3 to the power of 3 times 5 to the power of 3 times 11 to the power of 2. Okay, so as I said, you are given these numbers after the standard prime factorizations have been completed. So you don't need to use, factor tree to um, factorize them. So how do I determine the LCM? First, we copy down the numbers that are not in common, like I think 2 is not in common because 2 to the power of 3 appears in the first number alone. So I write here 2 to the power of 3. Also 7 is not in common. 3 to the power of 3 is not in common. And 11 squared also is not in common. The only thing that appears in both is 5. And which exponent will you choose for 5? The largest. You compare the exponents. See, I'm going to mark them 2 and 3. And then you choose the larger one, which is 3. I'm not going to evaluate this number. We are done here. This is the LCM. You can use your calculator to find the final answer, but it's not necessary at this point. Yeah, it's we applied standard prime factorization to find the LCM and GCF of two given numbers. More and more we do number theory, more and more we go forward, we'll see that how valuable is the standard prime factorization, and all those questions that look very difficult without the standard prime factorization will be easy if you know how to use the standard prime factorization. Thank you for watching. Next lesson, we'll go deeper into the concept of GCF and LCM.